In the previous lecture, we looked at the problem of contact angle hysteresis, and we found that when we have contact angle hysteresis, the contact angle can be different from the Young's angle. So we described this angle, the contact angle hysteresis, in terms of two angles, the advancing angle and the receding angle. And we said that in general, you will have an angle between these two extreme limits, but for a static problem. In any of the earlier problems, we have not looked at a case where the contact angle is moving, except for the case where we had fluid rising in a capillary tube. We had ignored one essential important point in that problem, which is the local dynamics near the contact line. We had broadly looked at it as a balance of forces, and that allowed us to determine what is the height of the meniscus rising in the tube. We will now see a problem very close to that problem of a capillary rise in a tube, but instead of a capillary rise, we'll be looking at a thin film down an incline. The primary reason for choosing this particular problem to illustrate some of the challenges in contact line modeling is that I can take advantage of the framework that we had developed in earlier lectures, primarily the lubrication approximation. I'll also use some earlier results we'll also use some earlier results where, for example, we'll be looking at thin film down, a uniform thin film flowing down an incline, and a snippet of that lecture is shown on the screen as well. So let us begin by looking at the problem down an incline. So we have a thin film far away from the contact line. We have a thin film of thickness D. But as it approaches the contact line, it tends to slightly bulge upwards and then eventually meets the plate. The interface meets the plate at the contact line. The contact line here for us is a point because we are looking at the problem in a two-dimensional setting. The angle is chosen to be, the contact angle is theta, and the inclined plane is making an angle of alpha. This alpha can also be vertical, and that's the kind of situation that we'll be looking at as well. So I've chosen the coordinate system to coincide with the plate. The x-axis is along the plate and y-axis is perpendicular plate. This is exactly what we had done in the earlier lectures. And for the case of uniform film down an incline, we had also got the velocity profile in the thin film, which we'll be using. So what are the primary goals of the lecture? So there are two goals. One is to derive an evolution equation or a governing equation for the thickness of the thin film, where we incorporate all the boundary conditions, especially the contact angle boundary conditions. The second one is to illustrate the challenges that one encounters when working with problems involving moving contact lines. In particular, we will see that if we apply classical boundary conditions, that is just no slip boundary condition at the wall, then we'll encounter a singularity at the contact line. And the singularity that we'll find for this problem is actually not a feature for this restricted lubrication problem, but rather it's a generic feature of all moving contact line problems. In a subsequent lecture, I'll talk about how certain modeling is being done to alleviate the singularity. This is still an active area of research, and papers as recent as in the last few years fundamental papers are being written on this problem. So let us begin by looking at a uniform film down an incline as an example. So here we had calculated a few weeks ago that the velocity profile follows has a half parabolic shape. And if we calculate the average velocity for that profile, the average velocity was simply 1 by h naught, 0 to h naught, u of y dy. And if we do the analysis, if we do the integration, we simply get 1 by 3. And instead of using kinematic viscosity, I'll use the dynamic viscosity. So that will be rho by mu, that's the dynamic viscosity, g h naught square times sine of alpha. So you see that the average velocity is given by rho g h naught square by mu times sine of alpha. So the component of gravity which is driving the flow is g sine alpha, and that's the driving force, and the retarding force is viscosity. So it's a balance of those two forces which will give rise to a steady state solution. Now, motivated by this average velocity, for our problem, we can choose a velocity capital U, which is given by rho g d square by mu sine alpha as a characteristic velocity. Let this be the characteristic velocity. Okay, we will be doing this in the lubrication approximation where surface tension is the dominant force over viscosity. So we can define a capillary number which is mu u by gamma. We will say this is much less than 1. So this is my, I'll label this, this is the capillary number for us. Now before I write down the non-dimensional equations, or maybe we need to understand how non-dimensionalization is also done. Or maybe I'll just write down the non-dimensional equations first. So the non-dimensional equations in lubrication approximation, or rather with lubrication approximation, they simply become Px is equal to Uyy plus 1. That's equation 3 for me. Py is just 0. That's 4. And continuity equation, that's Ux plus Vy is equal to 0. That's 5. So these equations 3, 4, 5 that you see are the lubrication approximation, the equations from lubrication approximation. These equations were also derived when we did the lubrication approximation, except that in some problems we didn't have gravity. So the idea of non-dimensionalization is follows. How do we do this? We do this by basically defining the following non-dimensional variables. Non-dimensional variables are defined as follows. X is the non-dimensional variable for x, and that simply becomes x tilde divided by d by capillary power 1 by 3. Remember, I said capillary number is very small, so capillary number 1 by 3 is also small, and y simply becomes y tilde by d, and u becomes u tilde by capital U, and v is v tilde by capillary number power 1 by 3 times u. And the pressure is taken to be the pressure inside the film minus the outside pressure, the dimensional outside pressure, divided by capillary power 2 by 3 times the scale for pressure, that is gamma by d, where gamma is a surface tension and time is simply taken to be T tilde divided by capillary power 1 minus 1 by 3 d by u. So if you are wondering how do I get this capillary 1 by 3 term, so this is worth quickly going through this because this is not really discussed much in standard textbooks. So this is we'll take a small detour. Non-dimensionalization procedure. So this detour I'll write it using blue ink, and we'll return to the regular set of equations later. So the idea is as follows. In Stokes flow, if we start with Stokes flow, we have minus grad P plus mu del square of U plus rho G is the Stokes flow, right? Now we can actually non-dimensionalize the following. We can just say x bar is just x by d and y bar is y by d, y tilde by d. And similarly, we can do the same thing for velocity. U bar is u tilde by capital U, v bar is v tilde by capital U again. So there is no variation. There's no, it's we haven't introduced the lubrication approximation yet. And if you write down the scale for pressure, we can simply take P bar to be some P tilde divided by gamma by D. This is, or we can even subtract the thing outside. Okay. So this is, of course, I'm not going to, I'm not be doing this rigorously, but I'll give you an idea of where this comes about. If you substitute these these variables into the equation that you would get would be, for the x component, let's say, x component, you would get something like this: minus del p by del x plus capillary number del square of u, these are all variables with a bar, plus rho g d square by gamma is equal to 0. This number can be called the bond number, often represented with written as BO, and we'll set it to be 1 without any loss of generality, which means that I'm choosing a thin film of a thickness D such that this quantity rho g d square by gamma is 0, is 1, where rho and gamma are material properties. G is something that we can't change. It is fixed by the in fact, it's fixed by the planet on which you're working on, and D is basically the parameter that you can choose. Therefore, I can always choose this parameter to be 1. And capillary number is just what we had defined earlier, mu u by d. And this del square operator is nothing but del square by del x square plus del square by del y square. This is a bar. Okay. Now note that I haven't really employed the lubrication approximation yet. Now we want to employ the lubrication approximation. So lubrication approximation for this particular problem is done as follows. We will just say the non-dimensional variable in the lubrication approximation is just P bar by capillary power m. We will say x goes like x bar capillary power n, and we'll say y is y bar. So notice that x bar is being multiplied by a quantity which is capillary power n, where we'll take n to be greater than 1, and we'll also take m to be greater than 1. Okay, so the idea is that x is very, very large compared to y, but in the non-dimensional variables, that is where we have x bar, we have x and y, we want them to be of comparable size. Again, let me repeat, x tilde and x bar are very large compared to y tilde and y bar, meaning the corresponding variables in the original coordinate system and the non-dimensionalization that we had done, which is x bar and y bar, they're very large, and there's a disparity. We want to address the disparity by recognizing the fact that when we take the non-dimensionalization, the non-dimensional variables x and y, I want them to be of a comparable size. How do I make them to be of comparable size? I'll say x will be x bar times capillary power, and because x bar is very, very large, to make x to be an order 1 quantity, I have to multiply it by a small parameter, that is x power n. The thing is, I do not know what is the value of n at this point. I also want to enforce one more condition, which is the condition of, I should maybe mention that if we have I forgot to mention the normal stress balance, because we have an interface here. In the original non-dimensional parameters, the normal stress balance becomes it simply becomes something like delta P. This is dimensional across the interface will be order capillary terms, capillary viscous terms. I will not write it here, but the viscous terms are all very small because we are talking at capillary number very small. Therefore, capillary number is the ratio of viscous to surface tension, and when capillary number are very small, it means that surface tension is much surface tension effects are much stronger than the viscous effects. And finally, we have the curvature terms here. On the curvature, we have something like h. We get something like h bar x bar x bar divided by 1 plus h bar x bar square whole power 3 by 2. This is the kind of term that we would get. Now we want to non-dimensionalize it. Now if we do this, now what's the logic for choosing n? M and n are chosen such that the final equations have gravity, viscosity, and surface tension. Equally important. So the idea is that when we do the finite analysis, we want to do it in such a way that all the three forces, gravity, viscosity, and surface tension, they're all equally important. So now we want all the three forces, gravity, viscosity, and surface tension, to be equally important. And if we want all these forces to be equally important, we can determine the values of m and n. So the non-dimensional terms would be as follows: del p bar by del x bar simply becomes capillary power m times capillary power n del p by del x, and capillary power del square u bar by del x bar square simply becomes capillary number times capillary power 2n times del square u by del x square, and finally we have capillary del square u bar by del y bar square simply becomes capillary times capillary, this is just as it is, del square u bar by del square u by del y square. Okay, so this is what we have. So let the equation essentially becomes, we're looking at this equation, let's call this as equation star. Equation star becomes, I'll write it right here so that you can see this. Equation star becomes minus capillary power m plus n del p by del x plus capillary number times, so what are the two terms that we have? Capillary power 2n times uxx plus uyy plus 1 is 0. That's what we have. So if I want to ensure that gravity, viscosity, and surface tension forces are equally important, at least what we can make sure that these we have to also write down the normal stress balance, and the normal stress balance simply becomes capillary power m times del p, again becomes order capillary viscous terms. These are small terms, so I'm not bothered about them. This will be minus capillary power 2n divided by hxx. The denominator would be something like 1 plus h bar x bar will be something like h power 2 h power n capillary power n hx. So therefore when n is greater than 1, capillary power n is very, very small, and therefore this term becomes, magnitude of this term is very small. Right? So therefore I'm not writing the denominator. So now we have two equations. The first equation is coming from the momentum equation, and the second equation is coming from the normal stress balance. So we want to ensure that gravity, viscosity and surface tension are all important. If you look at the normal stress balance, it tells me that the pressure term and the surface tension term have to be in balance. So in other words, pressure is really here the capillary pressure. So I now have, looking at the balance of these two, I have m is equal to 2n. If I look at the dominant term here, this term is going to be very small, and the second term is the dominant term. Therefore, I now have a balance between this term and this term. If I look at that, I get another equation which is m plus n is equal to 1. So I have two equations and two unknowns. M plus n is equal to 1 and m is equal to 2n. So if I substitute from this, I get m becomes 2n, 2n plus n is equal to 1, and therefore n gives me 1 by 3 and m becomes 2 by 3. So in other words, in the lubrication approximation, we had earlier used a parameter epsilon, right? Or rather, for this problem, epsilon is indeed capillary power 1 by 3. That's exactly the value of epsilon. Okay, so that sort of brings closure to our little detour that we've taken. Let's return to our original problem. So hopefully you can see the rationale for choosing a specific non-dimensional variables. These non-dimensional variables that we have, x tilde going like capillary power 1 by 3 times x tilde by d, and where pressure, we have a capillary power 2 by 3 in the denominator. This choice of non-dimensional numbers, this capillary power 1 by 3, comes by ensuring that pressure or the capillary pressure, viscous terms and gravity are all equally important. Now equation 3 tells me that the pressure gradient and the viscous forces have the same order of magnitude. That's why we have px, we have no prefactors in between, in front of them. Px is comparable to uyy plus 1. And when it comes to the boundary conditions, we simply have non-dimensional boundary conditions. We have the following. We have V will be ht plus uhx. This is our kinematic condition. This we'll call it as equation number 6. Then we have the condition at the interface, that is uy is equal to 0. This is the tangential stress boundary condition at the interface. And we also have P is minus hxx. This is the normal stress balance, the dominant normal stress balance, which we'll call it as equation 8. All these three conditions here, these are applied at y equals h of x comma t, correct? And we also have the boundary conditions on the wall, u equal to 0 and v equal to 0. We'll give them labels as well. So we'll call them as 9 and 10. These are basically at y equal to 0. So the full set of equations with the boundary conditions, I'll write them in one place. Governing equations would simply be Px is equal to uyy plus 1, py is equal to 0, and ux plus vy is equal to 0. So this was originally the labels 3, 4 and 5. So 3, 4, 5 essentially becomes a governing equation. 6 to 10 becomes our boundary conditions, right? So let's basically derive an evolution equation for the height. So we'll do the following. From 5 we have ux plus vy is 0, and therefore we'll integrate this to say 0 to some h ux dx, or sorry, dx dy plus 0 to h vy dy is 0. I simply have 0 to h ux dy plus v at y equal to h is 0, right? And therefore I can now substitute the expression for v from the kinematic condition using v at y equal to h from equation 6. We get ht plus uhx plus 0 to h ux dy is 0. That's my equation that I get. Now we can use Leibniz's rule. Leibniz's rule essentially says, for those who may not be very familiar with the Leibniz rule, it says if you have a quantity like this, 0 to, let's say, h of x, some f dy, this simply becomes the function at that location, f of h comma x, times the derivative of the limit, that is h of x, plus I go from 0 to h del f by del x of dy. This is basically my Leibniz rule. So I can just say, using f is equal to u, I simply get del by del x of 0 to h of x u dy simply becomes u times del h by del x plus 0 to h del u by del x of dy, right? Therefore I simply have 0 to h ux dy on the right hand side. This will simply be minus uhx plus del by del x of u dy going from 0 to h of x, correct? If I substitute this quantity here into the final equation that we had earlier, we simply get ht plus uhx plus minus uhx plus del by del x of 0 to h of x. This h of x is actually h of x comma t, by the way. Du dy is 0. I simply get an equation as follows: ht plus del by del x of 0 to h of x of u dy is equal to 0. This will give it a label. Our last label was, I think, equation 10. So we'll give this a label as 11. Okay. Now we can do some more things. we can integrate equation number 3. What was equation number 3 for us? It was px plus uyy plus 1 is equal to uyy plus 1. I will simply write it as uyy is equal to px minus 1. So uy will be px times y, or rather I'll just keep it as it is, px minus 1 into y plus c1, and u will be px minus 1 y square by 2 plus c1y plus c2, right? Now we can apply the boundary conditions. At y equal to 0, u equal to 0, and this gives me the constant c2 to be 0. We also have at y equals h, uy is 0, and this gives me the constant c1. This gives me minus of px minus 1 times h. And therefore I simply get u, which is a function of x, y, and t, will be px minus 1 times y square by 2 minus hy. This will give it, we'll call it equation number 12, right? We also have one more thing. We can basically substitute the expression for p in terms of the height from equation number 8. So we get using 8 in 12, we get u will be hxxx minus 1 times y square by 2 minus hy. This is an important result. So we actually got a parabolic velocity profile, which is driven by a balance of capillary pressure gradient and the gravity term, right? So we can actually do we can substitute this u into the equation number 11. Remember, equation 11 number 11 has actually come from kinematic condition. Kinematic condition itself is coming from a mass balance constraint. Whenever the interface moves up and down, which is given by h of t, we are essentially saying that if the interface, let's say, is going up, then the fluid has to rush in to fill that void, to create that bulge. So interface locally going up means locally creating a bulge, and the fluid has to bulge in. The fluid has to move horizontally, in fact along the x direction. That's why we have a relationship between the variations in the height to the variations of the x component of the velocity. Okay, that's equation number that was our equation number 11. So we can now substituting 13 into our equation 11, we simply get, we have to evaluate this quantity 0 to h u of y dy. I'll assume that this is a straightforward integration for all of you, so I'll write the final result. We simply have hxxx plus 1 multiplied by h cube. Therefore, del by del x of 0 to h u dy will simply be half hxx h cube, again with respect to x, sorry, not half, sorry, it's 1 by 3 plus h square times hx. This is what we have. If we substitute this into equation 3, we therefore get ht plus 1 by 3 hxxx h cube of x plus h square hx is equal to 0. This is again an important result. We have now equation number 14, and this equation 14 is nothing but the evolution equation, evolution or governing equation for interface shape. Okay, it's a fourth order nonlinear PDE. Remember, it's a PDE because we have variations in time and x. So it means that PDE, fourth order PDE, and we have 4 boundary conditions. 4 boundary conditions required in x and 1 initial condition in time. So that means I need to specify the initial shape of the interface at t equal to 0. That's my initial condition because we have a time derivative and we have 4 spatial derivatives. Okay. So let's take up this problem in the next lecture. The first part of the goal is satisfied. Now the boundary conditions would involve a boundary condition that the interface meets the solid at the contact line where the height goes to 0. We have to provide the contact angle condition which relates the slope of the interface to the contact angle locally. And then we have far field conditions where we have a flat thin film. So the flat thin film is where we can straight away say that the thickness of the film is uniform. It's at a value of 1. We can also say that as you go to the flat thin film, there are no variations in the thin film height. So that gives us the 4 boundary conditions. Some more thought has to be put into determining the initial conditions, but we'll discuss that in the next lecture. I'll see you around in the next lecture. Thank you.